Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, we will continue our discussion about waveguides. So in the last session, we discussed how to find the electric field and magnetic field component along the direction of wave propagation. That is Ez and Hz we have found. So we are going to assume in that expression that wave is propagating along the positive z direction. Okay. So in that case, one multiplied constant C5 is going to be 0 there. So in that case, my 10th equation is now going to get reduced like this. That is, constants get changed. A1 cos kxx plus A2 sin kxx. This term also remains same. Only thing is e power minus gamma z will be there. This represents wave is propagating in negative positive z direction. One more component is there, that is plus e power plus gamma z. So that represents wave traveling in negative z direction. That only we neglected by assuming that constant is 0. So we are now changing the constant C1 to C6 now to A1 to A4. So these are the values for A1, A2, A3 and A4. So by taking the similar steps uh, for electric field, we are going to find the component of Z for the magnetic field. Okay, Z component for magnetic field. So same expression we have to write it, but only the constant have to be changed from A to B. Rest remains the same. So out of the six wave equations for the rectangular waveguide, we have found two. Four more are left. Okay, the components of electric and magnetic field other than the direction of wave propagation, that is along x and y, I have to find. For that, instead of solving the equation, we can easily use the Maxwell equation and determine these components from the EZS and HZS component. Okay, so we know Faraday's law and Ampere circuit law, right? There we are going to take the time harmonic form expression and we are going to expand that del cross ES, right? So del cross E, we know curl of a vector. I can write first row unit vectors along the x, y, z direction. Second row is a partial differentiation. Third row I have to represent the components of E along x, y, and z, and that is going to be equal to j omega mu. For h's, I have to represent in terms of rectangular coordinates, hx, hy, hz followed by its unit vector. What I'm going to do here is we are going to expand this expression determinant. We know how to expand it, determinant, and we are going to equate the unit vectors on both sides. Okay, similar unit vector. So this is the first expression while equating the AX unit vector. So let us see, AX means first we have to take it and then multiply these two, right? Dou EZS by dou Y minus dou EYS by dou Z is equal to minus j omega mu HXS. Similarly, if I do for the Ampere circuit law this expression, I will get the same. Components will be same. Only instead of electric field, I have to represent the magnetic field. And what is on the right hand side is j omega epsilon EXS I have to change. Okay. Similarly, for the second component AY, okay, A is that everything is written here in the successive equations. Now what we are going to do, we are going to express that unknowns Ex, Ey, Hx, Hy. Okay, we have to include the suffixes to represent its phasor form in terms of EZS and HZS. That means take the second and third equation, that is 13b and c if you take. So j omega epsilon exs, I can write it as dou hs by dou y minus, instead of HYS, I can write, okay, the dou by dou Z remains same. Instead of this HYS, I'm going to substitute this term. So what will come here? For this, minus 1 by j omega mu will come. So it's going to be plus here. Already one negative sign is there. Then what comes? Dou EZS divided by dou square. Already one dou by dou Z is there. So dou square EXS by dou X, dou Z square. And here minus, what happens? dou square E z s by dou x dou z. So I think you are able to understand. So already from the 11th and 12th expression that we have seen, okay, we can understand that all the field components are varying with respect to e power minus gamma z. So I can write E z s. We already know it is varying with respect to e power minus gamma z. Similarly, E x s should be. Okay, so we are going to find these terms. That is dou E z s divided by dou z I can find. Okay, with respect to z, if I differentiate, what comes? E power minus gamma z into minus gamma I will get. So that minus gamma will be there. Instead of e power minus gamma z, I am going to substitute E z s only. For dou Exs by dou z square. So one time differentiation, I got this right. If I do the second time differentiation, what I will get? Again, I will get one more minus gamma. So minus gamma now turns out to be gamma square. Exs will be there. So we are just substituting instead of this double derivative gamma square Exs, and here already one negative sign is there, here negative, so plus gamma into dou E z, one term only we have found. Okay, dou E z s by dou z we have found. So dou E z s divided by dou x we have to write it. So what I'm going to do next is I'm going to combine the common terms. So EXS is common, right? So I'm going to take EXS term that is available here to the left hand side. Okay, and we are going to write the other terms, the differentiation terms on the right hand side of it. And we are going to do one assumption that gamma square plus omega square mu epsilon is going to be h square. Okay, and I can write in other way, that is gamma square plus k square, because k is the propagation phase constant. It's a phase constant that is equal to omega root of mu epsilon, right? And then EXS from the previous expression we can write as EXS is nothing but, if it comes to this side, minus will be coming here, minus gamma by this term coming to the denominator. So these terms get cancelled, right? So minus gamma by h square dou E z s by dou x. Okay, then if this terms come this side, so minus uh, j omega mu, it comes in the numerator part. Okay, minus j omega mu divided by this h square will be there as it is dou h is z by dou y. Okay, we have found the ex component. Similarly, we can find EYS, HXS, HYS in terms of EZS and HZS. So if you see, all the components are having EZS and HZS values. Okay, if you know these two components, that is electric field and magnetic field, along the wave direction, wave propagation direction. Okay, the wave is propagating along the Z direction, right? In the rectangular waveguide, if you know that component, we can find the other field components. Okay, where h square is gamma square plus k square, that we know, and that can be equated to kx square plus ky square. I hope everyone understood how to find the electric and magnetic field expressions for the rectangular waveguide. 6 equations in total, these 4, and 2 more we have started, okay, in the 11th and 12th expression. So in the next session, we will understand how to find the field patterns, different mode configurations in rectangular waveguide. Happy learning. We will see next time.